Good. So Safety 21 is the National University Transportation Center funded by the U.S. Department of Transportation. It's Carnegie Mellon is the lead, but we have these fantastic universities that you can see here that are part of the work that we do. It's a $20 million program funded by US DOT. It's focused on safety. And it's a safe transportation, also autonomous vehicles, connected infrastructure. That's why the work that Fernando, our guest speaker, is doing is so critical to the work that we do. Please check us out if you're not already getting my weekly emails on Thursday, the Smart Transportation Dispatch. It's our newsletter. If you go to our website, Safety 21 CMU, something like that, you can click and it's a great way to connect. We have a transportation club, so for students, if you're not already a part of that, please join. So this seminar series is an opportunity to showcase our work, to connect, ask questions. So our professor, Fernando, has said that it's okay to interrupt his question when he's saying that if you have a question today, so you don't have to wait till the end. So if you're in the room, you get to raise your hand. And if you're online, send your questions through the chat. And now I'd like to introduce our esteemed speaker, who is, thanks to Professor John Pija, we have Fernando Velez with us. He received his Master's of Science and PhD in Electrical and Computer Engineering from, my Portuguese is very poor, but the Instituto Superior Technical University of Lisbon. I won't tell in the 90s and in 2001. And since 1995, he's been with the Department of Electromechanical Engineering in Portugal. And I can't pronounce all those, but you can read them. Okay, fantastic. And he's assistant professor, senior researcher at the Institute de Telecomunicados.
No, I'm already associated.
No, okay. And let's see, you've authored 4 books.
Yeah.
Okay, 25 book chapters, 182 papers. Can you imagine? Imagine the editing of 182 papers. Okay. Lots of journals, conferences. We're so thrilled to have you here. He's one of the last times he was in Pittsburgh, it was sub-zero in January.
Minus 27.
Which is crazy. I don't even know what that is. I don't want to know how cold that was. So today, let's give a warm Pittsburgh welcome to Dr. Velez. Thank you. All right.
Now I have also a collaboration with something, maybe it's not the same scale, but in Portugal there is an agenda, a research agenda called Route 25. And there was recently some call for contributions, and Catherine Fanningen from EVP submitted a small proposal. It's just not a lot of money, but to collaborate with this agenda. But it's in the same line because they are addressing autonomous driving. They have their own car, they are testing the solutions and these things. So somehow in our collaboration with Catherine, we are starting something similar to this. But my student that will be in this project is doing something on smart parking for low density population regions, mountain regions. And we are getting inspiration from Europe and from USA to this. But the inspiration is something that is similar to this, maybe in a smaller scale. But anyway, for the Portuguese dimension, let's say, it's a big scale for us. Route 25.
Well, a lot of these problems are universal.
Yeah.
They're not just in the United States.
So we are starting also to address in this context something similar.
Great. All right, I have to step out. I'll be back. So you guys, you take good care of it, okay? I'll be back.
Thank you for your introduction, and let me start presenting my work. As Karen mentioned, you can interrupt if you have questions. This can be very interactive. And this is work we have been doing together with a student and another colleague from my institute, is the Institute of Telecommunications in Portugal. And this was a collaboration also with colleagues from Belgium. In Europe, we have the so-called cost actions. It's cooperative and scientific technological, and then we have some topic. Our topic is mobile communications, but the inspiration is to apply artificial intelligence to mobile communication in general. And these projects are not funded with a lot of money, but they allow mobility of researchers and students so that we can meet 3 times a year in one very nice location in Europe. And the students can travel to the other universities or companies to work for 3-4 weeks with the other teams. And my work is intelligent photoplethysmogram-based heart rate signals analysis for car drivers monitoring. And we are thinking about considering some sensors, and I will explain what was the basis of this. But then our colleagues from Ghent University were doing similar work just with one sensor, with the accelerometer, for orders, and they had experience on this and applying artificial intelligence techniques to this. And my student joined their group to learn from them and advance what they have done before with our own proposals. Okay. This is summary. Maybe this is not fully mapping what I have here. I was just preparing this today, but I think it maybe 95% fits what I have here. Problem approach, Internet of Medical Things, state-of-the-art answers to 4 research questions. This initial part is the part where we did systematic review. So before we started the work for maybe 6-7 months, we did a systematic review, used some tools, we used the so-called PRISMA approach, and we learned from what is in the literature. Even later on, because we are submitting it to ACM computing surveys, we received some suggestions, and we needed to update. We started this in 2022, and now in 2024 we updated this with maybe, in the end it was 2-3 more publications that were relevant for the study, but we updated. And then the second part here is proposed system materials, electrical schematic, PCB design, 3D model, device printed body. What the student did was to produce the electronics for a smart wristband, like a smartwatch for the solution. It's not really a smartwatch yet, but it's something that seems to be. And then in the phase of the work where we collaborated with a team in the University of Ghent, we considered deep learning models, sliding winning technique, data processing, the CNN architecture, convolutional neural network architecture, metric results, web deployment, mobile. Some of these I will give more details, some I will just briefly mention here, and then conclusions and future work. So the motivation for this work somehow is the great, this is for in Portugal, but the number of drivers are increasing, mainly young drivers. Nowadays in Portugal, maybe 40 or 50 years ago, most of the drivers were men, now are women, so the number of drivers is increasing also because of this. Young people, all of them, they have driving license, and we are a population of almost 11 millions, and more than 6 million have the driving license. So there are kids and other people that don't have. And the cause of most number of accidents is the psychological state of the driver. So, and this is influenced by also the health condition of the driver. If the driver is not in good mood, if he's tired or with stress or something, then something can happen. And in Portugal, more than in other European countries, traffic accidents remain a leading cause of death and serious injury, and particularly among young drivers. And with this annual flood of new drivers, it is crucial to educate them on potential hazards that contribute to these accidents. So this was the motivation of this work, and I remember that student came to me during the classes in the first year of the master, and he was trying to find a project topic, and then he started to talk with my colleague Ivan about this, and he came to the idea of proposing this. So this is totally his own idea for the research topic, and then gradually for the solutions. The automotive industry is shifting towards network systems to lower the accident rates and increase public safety. A great deal of research and study has been done on creation of new monitoring methods to assess a person's vital psychological signs at home, in a car, or in other non-clinical settings. So basically we are now using sensor, not in a clinical setting, but during the daily life. And in particular, we are considering this while we are driving. My car sometimes already tells me, oh, maybe it's better that you go and have a coffee after 2 hours. Maybe, I think when I blink my eyes, the car sometimes suggests me, even if I'm talking with my wife, but I blink the eyes and, oh, you are sleepy. Sometimes I'm not, but it suggests me to go to have a coffee. And this is the kind of research that is needed to improve this and to prevent the risk of accidents. And here in this figure on the left-hand side, we have this context of the Internet of Medical Things, monitor patients, ambulances, car takers, smart wheelchair, different things, and then the diabetic device on the right-hand side, and then it can communicate with the hospital, with the nurse, with the physician, through health apps, and there is now a lot of wearables that can monitor the health condition. When I was here, part of the work in 2016, I was preparing a edited book with João Paulo Cunha, who is a colleague that is coming. He did the research, important research in Portugal, of the vital jacket for the fire brigades, and we published a book on wearable technologies and the applications of sensor networks to body area networks in different situations. So this is kind of research. I'm fortunate to have one department of textile engineering in my university, so that we could cooperate in some fields where we could produce even electronic and software solutions for some applications. And the challenge of Internet of Medical Things are span from environmental impact, cost efficacy, power consumption, interoperability, data management, scalability, upgradation, regulation and standardization, and privacy and security of data. And what we did prior to the study itself and development was to perform a systematic review. So we started, I don't know if you can read, but we had more than 18,000 records, and we had took this Prisma approach. Prisma stands for, in the second bullet, let's say, for the a framework for preferred reporting items for systematic reviews and meta-analysis. And many of the researchers nowadays around the world are using this approach. And this is a natural language processing framework. And after this, we did some screening. After duplications have been removed, we decreased from 18,000 to around 14,000 papers, and then some screening, reading the abstracts or the titles. We remove more than 243, and then we addressed the abstracts for eligibility, and in the end we came up with 164 studies for the qualitative synthesis, and after this 235 studies for the quantitative synthesis meta-analysis. The studies were from following scientific database like IEEE Explore, Springer, Science Direct, it means Elsevier, ACM, Multidisciplinary Digital Publishing Institute, MDPI, and PubMed Central. An inclusion criteria for the study was applied to the three studies was consist of healthcare monitoring, 1, make use of wearable devices in IoT environment, 3, benefit from one or more embedded sensors, 4, present the purpose of the study, characterize the population of the study, present precise results about healthcare monitoring and application, present original research were published between 2010 and 2022. Then in the review, the revision we did after the second round of reviews, also until 2024, and were written in English. We are in Portugal, so sometimes you find many things, many papers written in Portuguese, in Spanish, also Portuguese from Brazil. Brazil has more than 200 million people, so it's, there is a lot of publications also there. And main questions to be answered, and then I will present in detail. Today I was preparing some slides for the answers to these questions to share with you. Are the main questions to be answered by the systematic review are the following ones. Which methods are used to detect individuals' vital signs? Which sensors are used for measurement? So methods and then sensors. And third, how do such methods impact individual performance in a driving situation? And 4, which technologies could improve the driver's security? And then we identified, here I put the numbers of figures from the systematic review. Then in other parts I will have the number of the figures for the thesis of my student. But I kept this. So the bar representation of the number of studies for each of the features used. Body temperature, heart rate, SpO2. This is a test that we can do putting some device in our finger. SEG data, so these are the most ones, respiration rate. Then there are studies for blood pressure, vital signs, pulse rate, skin temperature. But we identified maybe 13 studies for the heart rate. So this is the quantitative values of these studies. Then this is the representation of the number of studies for each type of communication. ANT is a protocol or a communication that is being used by the ANT wireless, which belongs to Garmin. So every of you who has a Garmin watch to monitor what you are doing exercise, use this protocol to connect from this band to the smartwatch. Zigbee, 3G network, Bluetooth low energy, Bluetooth, Wi-Fi. And then in the right-hand side, you have a bar representation of the number of studies for each of sensors used. And then we consider tablet, GPS sensor, because these devices nowadays have already a lot of sensors included, and we are monitoring our health, our behavior with this LED, LCD display, Raspberry Pi, SpO2 sensor, respiration rate sensor, radar sensor, smartwatch. So everything was identified here in these studies. And we had tables with the description of these characteristics. And what I did this morning was to present our, just in a not very structured way, but I tried to have it here. The research question 1 was, which methods are used to detect individuals' vital signs? Our study revealed a significant variation in methods depending on the specific application and target health metrics. Most studies utilize a combination of biosensors such as ECG, SpO2, and temperature sensors embedded in wearable devices like smartwatches, fitness trackers, and smart clothing for continuous data monitoring. Smartwatches, for instance, can track heart rate and SpO2 levels, while smart glasses may include sensors to monitor eye movements and detect signs of fatigue. These devices capture real-time physiological data, which is then processed using algorithms for signal filtering and feature extractions to ensure accurate and reduced noise. So here we started by reading all these papers and organizing them, and starting to identify what is important. For instance, this part of the filtering is important, and the advantage of our CNN algorithm, the application of our CNN, was because my student did 2 phases of filtering before he applied this, and improved the quality of the data very much with filtering. And these keywords are appearing here now from the previous study, from the literature review. The data collected is typically transmitted through low power communication protocols like Bluetooth or Bluetooth low energy. And in fact, the microcontroller for our solution that it's from Nordic Semiconductors includes the BLE technology. So it can communicate, for instance, with a mobile phone, but some sensors that as BLE can also reach the smart wrist with the data wirelessly. So they have Bluetooth or BLE to a central processing unit, often a smartphone or dedicated server where the advanced analytics are applied. This approach allows for continuous non-invasive monitoring of vital signs. For research question 2, which sensors are used for the measurement, we found that the analysis study employ a range of hardware components tailored to their specific application. The function of sensors vary from measuring vital signs to assisting in different ways. Most studies utilize ECG sensors to collect individual data, while other commonly used medical sensors included pulse oximeters and temperature sensors. Furthermore, movement and location sensors are often employed to provide supplementary and valuable information, enhancing the overall monitoring system effectiveness. Research question 3. What impacts do such measurements have on individuals' performance in a driving situation? So now we are already considering the driving situation. The review studies emphasize the importance of integrating a comprehensive monitoring system for individuals while driving. Implementing artificial intelligence capabilities offers significant advantages that can improve the driver performance and safety. For instance, AI-powered applications that use GPS can offer real-time information about the driver's surroundings, enhancing situational awareness and decision-making. Moreover, systems that alert healthcare professionals about driver vital signs enable timely medical interventions, thereby preventing potential health emergencies. These technologies collectively contribute to better physical and mental health by providing accurate, actionable information and ensuring a safe driving environment. Research question 4. Which technologies could potentially improve driver security? It is clear that modern healthcare technologies will play a crucial role in advancing driving systems. These applications have already become indispensable in people's daily lives, from fitness trackers to sleep monitoring devices. Similarly, applications designed to enhance driver security and well-being are undoubtedly essential in driving environment. By gathering and analyzing data, these technologies can make informed decisions that assist the driver, creating more intelligent and collaborative environments. This is achieved by efficiently managing travel and health information through various advanced features. For example, AI-driven applications can significantly enhance driver security through stress detection and management, as AI analyzes physiological data to identify stress levels and implement preventive measures. Fatigue detection systems utilize ocular metrics to monitor signs of drowsiness. I think this is what my car does to me, alerting the driver or taking preventive actions to prevent accidents. Also from the research question 4, integrating AI with other technologies such as GPS and vehicular sensors enhance situational awareness and decision making, ensuring a secure driving environment. Additionally, incorporating vehicle dynamics and cabin conditions such as temperature and air quality can provide a comprehensive view of drivers' health and environmental factors. This integrated approach is essential to optimize system performance and deliver actionable insights. These innovations collectively contribute to a safer and healthier driving experience by providing accurate, real-time information and enabling timely intervention. So this is part of the final, one of the final sections of our systematic review, where we answer to the research questions after the study with these more than 20 studies that we identified. Here we added more, so it's now 35, in fact, because when we updated this to 24, this increased from 32 to 35. Now, the next part, now it's what we did after all this systematic review of the literature. Accuracy of wearable device. Wearable devices offer valuable insights into the driver's physical and physiological state. They are connected, the physiological state and physical, but then they are also influencing a lot the psychological state of the driver. A great estimation of physiological signals is imperative to ensure safety drivers on the road, and the quality and accuracy of these signals can be significantly affected by various factors such as noise, artifacts, and device synchronization issues, especially in a driving environment. The driver is always moving, and the car is moving, and so on. And the layout of this conceived driver health system includes things, I don't know if you can read there, like communication, health, device and sensors, driver in center, medical staff, mobile application, cloud computing, edge computing. So all of this is involved. And the system overview includes number one, device layer, then the communication layer, then edge computing layer, cloud computing layer, application layer. The driver health system consists of a wearable device that can track several aspects of driver's health, process the data using smart techniques in real time, and provide the user with essential health information, as well as alert professionals in the health professionals in case of any critical situation. The primary purpose is to deliver a comfortable, high performance, and easy to use device that includes a mobile application with features that help users monitor their health and improve their well-being. And the materials that we identified span from microcontroller to the memory, and includes the heart rate sensor. This is the photoplethysmogram, PPG, optical sensor with a LED drive and a photodiode for green light detection. So it does green light detection in our wrist to detect the heart rate. IMU, this is a 3-axis accelerometer. Pressure sensor, a fuel gauge that includes a part from the precise measurement of the precision measurements of current and voltage, also the temperature, so it has also thermometer, let's say, the battery and the memory. Okay. And then the student produced the electrical schematic of the circuit, and in fact this is a small board to use in a wristband, and we are in some seminars, in some collaborations, we are also discussing this with other colleagues from Portugal, and they could have ways then to integrate this even more, to save energy, to save the power of battery and these things. So this is just a prototype, initial prototype that can be improved. And as these schematics are divided into 3 main parts: microcontrollers, sensors, and power. This is the microcontroller schematic, and then the power and the sensor schematic. And the top layer of the board of the PCB design is the red one, and the blue one is the bottom layer. Device board consists of 4 layers. Top layer is assigned to the signal and placement of the components. One of the inner layers is responsible for voltage, power, signal used for the components. The other inner layer serves as a reference ground for all components. Finally, the bottom layer is the RF paths reference ground and return noise path. For instance, this, I don't know, snake-shaped form is the antenna. Normally, even the boards, normally for the ISM bands already exclude this from the beginning, and we start designing from with some design that already includes the antenna because it's always needed. And this is the 3D model of our circuit, and this was every part is arranged in a elaborate manner to guarantee effective signal routing, reduce noise coupling, and optimize device overall performance. And this is the box. We did this with 3D printing, and in fact, maybe half or more than half of the volume is for the battery yet. So in the future, we need to optimize a lot the energy for this. Designed body is comfortable and adaptable straps are fitted to keep it to the user's wrist. In addition to the device, the battery will also encapsulate in the body. And then the study proposed, we didn't perform the study yet. We used, in this phase where we collaborated with the University of Ghent, we used data sets that are already available in literature to train our model and so on. But the study proposed involves a large enough sample size. The participants and a large enough sample size should be available to produce results with a 95% confidence level, direct contact with individuals, statistical analysis, a database for subsequent statistical treatment using SPSS software will be created, data characterization and entry error detection, hypothesis tests for qualitative variables to evaluate the system, and protocol, initial inquiry about personal data and state of health, test on a specific group of chosen individuals, moment 1, data collected analysis, finding validations with new experiments on the same individuals, moment 2. We got a permission from the ethics commission from our university to perform the study. Also, we have done it here. Normally, we need to have this permission to do this kind of stuff. And then the deep learning model. Now, this part is about the deep learning model. The PPG heart rate estimation model leveraging CNN, a convolutional neural network architecture, is designed to deliver real-time, accurate data readings based on PPG and accelerometer sensor data. By incorporating accelerometer data alongside PPG, the model provides a robust and reliable solution for users. The idea was to have data sets, and not online, but from these data sets to create some model that then can be applied in the real situation. So we use these data sets and train the model, and the idea when we can get our own data is then to retrain and learn more from it and start then using this. And we have this raw art data, and then we have a sliding window technique, then a data pre-processing technique, and this was the contribution from my student. The data pre-processing techniques include data resampling, real fast Fourier transform, Z normalization, isolation filter, low pass filter, and data shifting. And all of these allow us to have much better results than the ones that are in literature, because we did step by step all these pre-processing steps or techniques. Then the model architecture. You cannot see the details, but I will show in one of the next slides, and then mobile application. My student also was producing the application and could show something, but this was in a very early stage, but we have also this. We considered, I have another slide, but it's not here, but it's okay. We considered the PPG Dahlia dataset for training and evaluating the deep learning model. Integrate PPG, accelerometer, and temperature data. So this is also included. So as input and ECG data for labeling. So the idea here is that we have the device and simple data, but by learning, we could in our model then have take conclusions that are very similar of having a true ECG. So the idea is to create models that with simple data that we can get from the sensor that we have in our wristband to learn in a much better way. Data synchronization shift through a double tap gesture by subjects, consists of 15 subjects, 7 male, 8 female, with an average age of 30.60 plus or less 9.59 years old. Follows a defined protocol with 8 activities, including driving, aligned with project focus. So this, in the Dahlia dataset, the PPG Dahlia, they were doing different activities, but one of the activities was driving, so this aligns with our goal. Sliding window technique. The data was pre-processed by combining PPG, 3-axis accelerometer, temperature, and SCG data points into a single vector. This vector format facilitates efficient access and processing. Since the data represent a time series, we employed a windowing technique to segment the data for each subject. We used a window size of 8 seconds and a window shift of 2 seconds. This process creates segments of data for each subject, which are then fed into the model for training. So I have here an example. The data set was organized into 8 segments of PPG, and here we have different subjects. 8-second segments of PPG, so temperature and electrocardiogram data. This segmentation facilitates the process of visualization and analyzing the signal property of each subject. So then we have all the data set. This is just some part of it, but you can see all the sets of data that we have here. Data frame representing the segment of sensor data for subject 1. Each segment corresponds to an 8-second interval of PPG, accelerometer, and temperature and ECG data. So this is just for you to understand what kind of data we have. And then we have here the PPG raw data, and we applied also the 3-axis signal for the accelerometer data and the accelerometer magnitude. And here, this is some representation of the distribution of PPG values across several arbitrary segments, highlighting the variations and inconsistencies among them. Here we have in different colors, third segment, second segment, 15th, first, 10th segment, and we can see that for the different values of PPG signal intensity, we have some, in some cases, for different segments, the values are similar, but in some other cases, there is some inconsistency between the values of for the different segments. And then this was, for us, we consider that this was the most important part of our contribution, because compared to other studies, we did this data pre-processing and we improved the learning model. So these additional pre-processing techniques to prepare the input data include the synchronization of PPG and accelerometer data sampling. So they were not having the same clock, let's say, so which helped aligning both data sets and facilitating data analysis and interpretation, and data shifting operation to ensure proper synchronization between PPG and accelerometer signals, followed then by an isolation filter that was designed to subtract the accelerometer values from PPG data, freeing PPG signal from getting influenced by the accelerometer. So the two signals are interfering between each other, and in this pre-processing step, we isolated them in order to have the proper ones. And the blue curve is the isolated PPG after we extracted the accelerometer data from the interfered PPG, which shows in gray. Okay. And then we also applied a low-pass Butterworth filter with a cutoff frequency of 4 Hz, and an order of 5 was applied to the PPG signal. So in gray we have the raw PPG, and the filter PPG is in blue. So after this we also did final data preprocessing, applied some final data preprocessing techniques to the input data, real fast Fourier transform, RFFT. This proved to be an optimal choice to convert data from the time domain to the frequency domain, enabling analysis and processing in terms of frequency components. The RFFT frequency spectrum is located to a 0.4 Hz range, since there is a great concentration of data in this range. This ensures that the data supplied to the model contains the necessary features for precise analysis interpretation. Finally, Z normalization was performed on both the PPG signal and 3 channels of the accelerometer data, ensuring that all features are consistently scaled and that input data is appropriately prepared for efficient processing by the model. And here we have the time spectrum and frequency spectrum, here the accelerometer data, the PPG data, and on the other side we have the RFFT accelerometer signal on top for the frequency spectrum, and in the bottom we have the sensor data in the frequency spectrum for the RFFT of the PPG signal. PPG signal there, the accelerometer signal on top, but in terms of frequency spectrum. And then finally, after all these steps, we got the PPG final array that we used. And my student, João Pedro Baiense, was using the models developed in the Anaconda environment using Jupyter Notebook and Python version 3.12.3. Various Python libraries were employed in loading, processing, and visualization of data, such as Flask for the development of web applications, NumPy for the heart rate analysis, Keras for the implementation of deep neural networks, Matplotlib for static, interactive, and animated visualizations, NumPy for numerical computing, Pandas for data manipulation analysis, SciPy for mathematical functionalities, Scikit-learn for a two set of data mining and analysis, and TensorFlow for building and deploying machine learning models. And the versions are there. This I think I can jump. For the convolutional neural network model, we consider this paper from 2019, deep PPG large-scale heart rate estimation with convolutional neural networks. And in fact, this is considering some information for the heart rate that varies maybe from 1 to 3 Hertz. 2 Hertz is I think 1 Hertz is 60 beats per minute. 2 Hertz is 120 beats per minute. 3 Hertz is 180. And then when you are of my age, your Garmin starts to say if it's more than 180, stop, you are dying. but when I was young, and maybe now still sometimes, you can go up to 200 beats per minute. It's 3 something hertz, okay? And we consider these different phases of the applying some convolutions in different steps to then to have a model, less complex model. We had a flattening layer in the final part, and with fully connected layer, connect neurons in the last part, FC1, FC2. Here I'm presenting this with 1025, but in fact this was from the paper. We considered one that I mentioned before in the last, but we consider here 66 segments, and we considered here FFT, the channel and segment, and channel is X, Y, Z, okay? And finally, after the fully connected layer, we obtain just one value, which is HR, the heart rate, okay? So this is what, in a simple way, a simple explanation, the CNN model undergoes a series of layered computations, ultimately resulting in estimation of the heart rate as the final output. And this is the figure that my student is using, but I prefer this one that I produce myself and I can explain better. And this is the paper, the algorithm that is presented in the paper, the convolutions, the flattening, and so on, okay? The first convolutional layer performs fusion of the input channels, PPG and accelerometer. The second convolutional layer performs fusion of the segments involving the heart rate tracking. The subsequent convolution pooling layers serve to increase the learning capabilities of the model. And the last convolutional layer is included to reduce the input dimension of the fully connected layer, limiting model parameters and training time. Finally, the last fully connected layer outputs one value, which is the estimated heart rate. And the metric results include utilizing iterative processing involving data pre-processing, fine-tuning model hyperparameters, employing k-fold cross-validation, implementing early stopping. Development of our final model culminated in successfully estimating great reliable heart rate values. This was offline with data sets. Then what the aim is to use then the model in the real time. This model is configured with NEL equal to 6 and FC equal to 1024. The meanings of these were introduced here, the NTR and the NFC and these things. NFC is there in the fully connected layer one. Is the size of the fully connected layer. And N epochs 1500. The model's performance is reflected in its mean absolute error result of 3.50 plus or minus 1.32 bits per minute, and mean squared error of 69.5 plus or minus 93.6 bit per square meter to the square. And this was an improvement of around 54%. I will mention this in conclusion. Our student, João Pedro, also developed the mobile application. It provides a user interface and user experience features to interact directly with the device and displays crucial data about the driver's health condition. The start screen is the primary interface upon the application launch. The screen validates the activation of BLE and location of the device. BLE stands for Bluetooth Low Energy. Connects to the device and transitions to the home screen. The home screen serves as a central hub for assessing critical sensor data and pertinent user information in real time. And this is, in fact, we had the board, but then we broke some wire there that we could not repair. But there is this developing board here where we can connect the sensors. And anyway, this board is used to program our one. And we did some experiments with the app, just with this one in the app. Implementation of driver health system, featuring the prototype board connected to sensors and the driver health application displaying real-time data. The heart rate estimation model was transformed into a TensorFlow-like model for integration into the application, enabling users to estimate their heart rate values based on real-time sensor data. So, a deep learning model for estimating heart rate by leveraging PPG and the accelerometer that was presented. Initial training and validation of the model were conducted utilizing PPG dataset. By integrating multi-processing steps, include data analysis, signal insights, and the application of various techniques such as filters, complex algorithms, and data manipulation. Outstanding results of mean absolute error of 3.45 plus 1.324 BPM and mean square error of 69.5 plus or minus 93.57 bits per minute to the square were achieved, resulting in a 45.9% improvement in mean absolute error from the original study. The model aims to deliver estimations derived from sensor data, ensuring the fidelity and accuracy of users' health metrics. the research integrated the model into a user-friendly mobile application and will allow users to select specific data segments for analysis and visually presenting the results, which enable users to examine their health status in real time. These findings highlight the significance of meticulous data analysis and processing in wearable device applications and the high accuracy of the proposed model. And these are the acknowledgements. Mainly, it's a Portuguese project and the cost interact cooperation framework in Europe, where we supported the short-term scientific missions. STCM stands for short-term scientific mission from João Pedro to the University of Velez. Thank you very much. Now we have time for questions. Yes, please, John.
I'm curious where this information is processed. This is very sensitive information with big privacy implications. If it's stored and processed inside my car, I'm less worried, or does it go off to a remote server?
This is just in your wristband and your mobile phone.
Okay.
Then it can go to the hospital or to the whatever. But, the required permissions are needed, of course. But this is in your own personal devices, like you are using when you go for gym or for jogging or
And then I
something.
can set it up so it automatically notifies the hospital when I go to the gym.
Yeah, but it can just tell you maybe it's better to stop and go for coffee. This is the smarter way to warn you that you need to rest for 10 minutes and then recover.
A question, following up on that, the idea of safety and also privacy. In some countries there, especially for long haul drivers, like truckers, there's been the idea of, a lot of different assistive devices, but also requiring monitoring of the health and then having that data go to the company. Is this something that you've encountered in Europe, or what is the stance that you've heard and that you experience in Europe in terms of gathering that kind of information, health information about individuals as related to their employment and then processing that information?
From what I understand, in Europe, in Portugal, what we do is there is a doctor for the company, and normally the health information goes to the service. So for the doctor, to the nurse. So normally you need to have some medical protocol, let's say, or some, and it does not go to the boss or it goes to the medical staff of the company or to the medical company that works for the company. So I think this is the way. So medical information goes to medical staff somehow. This is at least our understanding. To the nurse, to the hospital, whatever, but I think this is the way. Do you have some online questions or?
I do not have any questions on that.
I'm curious about, so the sensors and accelerometers that you use, are these all off the shelf, or are you doing some retrofitting, or just trying to understand the actual hardware?
Yeah, it's for off the shelf.
It is, okay.
But now, this academic year, we are starting to have some projects to monitor breast problems like asthma or some, I don't know the name in English now, but respiratory problems, the ones that where people and another master student is doing another study, which is to monitor the health of a worker in a factory. And for this, in our department, because it's electromechanical engineering department, we are addressing to produce some sensors in the materials lab. So we are, the students are doing some literature review to produce our own sensors to basically what there are some tests that are being done nowadays in the hospital with maybe in English it's the wristband-based maybe, and they need to use it in the hospital, and with this which can monitor the expansion of our thorax, we can then make some predictions in real time while climbing the stairs, while working or something, and we are addressing these two scenarios. One is more for monitoring the respiratory problems, and the other is more to monitor the health and the condition of a worker.
All right, I love that, thank you. I love that it's off the shelf and then you're using it for novel applications.
Yeah.
Yeah.
But we are also addressing new sensors and also with chemistry and biochemistry colleagues also to have some new sensors to put on the skin, and so we are also addressing in a broader team the possibility of producing our own sensors that are not yet available.
Thank you. I think there's a question from the audience. Joy? I saw something come through.
Has there been any validation of the software, understanding that a comprehensive validation would be difficult to do?
This was developed in the team. I don't know exactly what you mean by the validation, but there was all these different steps, the using of all these tools, and I'm from telecommunication. I'm a telecommunication engineer and a researcher, but my other colleague Ivan, that was also supervisor, is from computer science, and he was working together with Ivan in this part. So, and the team in Ghent also had this experience, but this was just work for his thesis, not we didn't have a complete validation, of course. It's still somehow ongoing work. I don't know if I answered to the question.
Thank you.
I need some questions from the SEMU Portugal students in the audience.
You mentioned at some point that you're looking into prolonging battery life for that. I can imagine with all the sensors that are going to attach, how big do you imagine the improvements to be, and how long is it at the time right now?
From the discussions we had with the researchers from the other institute, it's INESCI. In fact, it's the institute that is coordinating the SEMU Portugal program. There is room for a lot of improvements. So managing the power, choosing other components for the devices, assembling them in a different way, and so integrating the solutions, and so there is a lot of room to improve this, and then possibly using smaller batteries. The goal is also to pack this. So from the initial prototype to something that is close to a product, many things in wearable technology, many things can be done. And in this team, they are specialized on doing this improvement. So there is a room for a lot of improvement.
I was just imagining, especially if it's a handheld device at the end, having heavy weight kind of.
Yeah. Yeah. Then you don't need to go to the gym anymore. I understand. Some days ago I did something overnight to manage my breath, and it's heavy. Even when you are sleeping, only in the morning I thought, oh no, I'm comfortable with this, but when I went to bed, it was not comfortable, and it was not very heavy at all, but it's uncomfortable. So if it's light, it's much better, of course. It's 4 o'clock. Thank you very much.
Yeah, thank you, speaker. Thank you so much. This was really, really great.
You're welcome.
Thank you to everybody who's joined us online and in person. Today's presentation will be posted on the Safety 21 website. It's called What's Happening, that we feature great events like this that we had here
Thank you.
today. And again, if you aren't already a member of the Transportation Club, we encourage students to join. It's a great way to get connected with other students who care about transportation beyond engineering too. So computer science, policy, sometimes even like, you know, philosophy. So thank you so much. This was great, and everybody have a great weekend. All right. Bye-bye.